T map it maps from the data point to the corresponding ground truth. For classification problem in this semester, we have introduced visual linear discriminant neural network, AWS, SVN, and some linear classifiers such as logistic regression. We also consider several famous or representative regression techniques, including polynomial curve fitting, Bayesian regression, neural networks, and support vector regression. So this is the focus of this course. Given input data, we have the ground truth we predict is a ground truth. So this is a supervised learning. Now let's look at unsupervised learning. We know most of us are lazy. We don't want to label the ground truth for the training data. So there are some famous unsupervised learning algorithms. They are developed to deal with unlabeled training data. So according to this notation, we just have the training data points, but the ground truth label is not available in unsupervised learning. So the goal of unsupervised learning is changed. We want to learn some underlying hidden structure of the data. So we don't learn a function to map the data to the ground truth. We just want to discover some hidden structure. This is the high-level description, but there are several unsupervised learning tasks, such as clustering, dimensionality reduction, density estimation, data reconstruction, or data generation. All of them deal with different hidden structure. So in the following, I will give a rough description about each of the 5 tasks. However, in this lecture, due to the time limitation, I will focus on 2 representative clustering algorithms. First of all, let's look at one of the most important unsupervised learning tasks. It is called clustering. Given a data set as input, we want to partition this data set into several clusters. So each cluster is a subset of data. After divided the data set into several clusters, our goal is that data points in the same cluster are more similar to each other than to those in other clusters. Here is an illustration. One point is one point is a data point. Okay, so it is unlabeled data set, so we don't have the color in the given the training data. We use k-means clustering, and we set the value of k to 3. So we will divide the whole data set into 3 clusters. This is a cluster red, a cluster green, a cluster blue, and a cluster red. So as you can see, data point of the same cluster are near to each other. So this is how the goal of clustering is to divide the whole data set into several clusters. And the cluster in this example are disjoint. Okay, so there is no shared data point in a pair of clusters. Okay, so this is the so-called hidden structure for clustering. We want to identify the hidden structure clusters. We also talked about dimensionality reduction in the previous two sessions. We specified Pca and the MDS. As you please record that for Pca, we are given a set of high dimensional data. We don't have layer ground truths, or we don't have layer or labels. So this is the it is an unsupervised dimensionality reduction measure. Similarly, MDS is also an unsupervised dimensionality reduction algorithm because we just have a pairwise distance among the data point. We don't have a layer label. So both Pca and the MDS are unsupervised dimensionality reduction measure. We want to project the data from a high dimensional space to a low dimensional one based on some criterion. This is Pca. This is also this is another unsupervised dimensionality reduction algorithm called the ISOMAP, LLE, and MDS. All of them are unsupervised dimensionality reduction measure. So in this application, the hidden structure is the lower dimensional space or lower dimensional manifold. Okay, so this is the goal of dimensionality reduction. Let's look at the another important application of unsupervised learning. It is called density estimation. So given a set of data points, we want to estimate the underlying probability density function. So this is an example. We have given a set of data points. Here are some red points. They are the given training data. We have a set of two-dimensional data points. The first dimension and the second dimension. So this is a data set on a two-dimensional space. We want to estimate the probability density at each location of this two-dimensional space. For example, we want to estimate the density here, and the density at this location. So as you could see, if you use a famous algorithm called the kernel density estimation, we use the third dimension to represent the estimated density. So we use the contour to denote the label of density. So you at each location you will get the value over the third dimension. So this is the estimated density. Now let's look at another application of data reconstruction. One famous example is the autoencoder. Actually, we can use a variant of artificial neural network. We have introduced neural network in some lecture. Autoencoder is also it is a variant of neural networks. Here is the input neurons, and here are the output neurons. So as you could see, both the numbers of input neurons is the same as the number of output neurons. Actually, this is the neural network. They try to reconstruct the input data. So the goal of the neural network is try to the goal of autoencoder is try to learn a neural network such that the output of this neural network can be similar to the input data point. So as you could see, this is a multi-layer neural network. This is the bottleneck of this neural network. We just have a few neurons. So in this process, we can use just a few neurons to to capture the most important property of the input data point. And we just use the important properties to reconstruct the input data points. So this is the process. This is a widely used process to pre-process the data or perform some data analysis. Here is the latent code of the data. So data reconstruction is also a task of unsupervised learning because we don't have the label of the input data. Our goal is to make the output as similar to the input as possible. Autoencoder is a variant of neural network, but I don't have time to give the detailed description. So as you could see, it is composed of an encoder and a decoder. Here is the encoder. We try to reduce the dimensionality of the data point. We just want to have a raw dimensional latent code to represent the data. And the decoder is here. It is used to convert the code to the data point. If we can carry out this effect, it means that encoder can extract the important feature of the input data point, and the decoder can recover the data point by referring to the compact code here. Another important and facing unsupervised learning is called data generation. In the era of deep learning, this branch has made a revolutionary impact. So let's look at the task of let's look at the definition of this task. We want to generate new data. For example, we want to generate new image or a new voice or other types of data from a complex high-dimensional distribution. And this distribution may be implicitly specified by a set of real data. Here is the example. We have some real image. So as you could see, this is an airplane, a bird, and a car. And we want to synthesize some new data. Actually, they are fake. They are synthesized or they are generated. They are not a real image. However, we want to make the generated data similar to the real image. Okay, so this is the goal of data generation. We want to synthesize new data. So here are two examples. Here are some digits generated by computer algorithm. Here are some generated face because they are not real face. We want to generate faces. They are similar to real faces. So this is the task of data generation. We just given a set of real image. We don't have the ground truth of the image. So this task belongs to unsupervised learning. Okay. In the following, our teaching assistant, Jimmy, is going to announce homework number 4 because I don't have sufficient time to introduce the two algorithms for clustering. Do you have any question for today's lecture? 各位同学，我们接下来我们的助教Jimmy 将会公布作业式。那在公布作业式之前，我不晓得大家有没有什么问题。By the way, Next week, I will go to the Ministry of Science and Technology, so I may not offer online lecture next week. I will provide a pre-recorded lecture, a pre-recorded video for the lecture next week. 各位同学也跟大家提醒一下哈，我们下个礼拜我要去科技部。那本来我是想说前2个小时可以就是线上授课，然后最后1个小时提供这个录影的这个 video，可是因为时间这样子弄比较赶，所以后来我经过考量了以后，我决定就是会先事前或事后提供这个就是3堂课的这个录影啊。大家有没有什么其他问题呢？那如果没有的话，那我们就让Jimmy 来公告这个作业式。
Okay.
Hey Jimmy, now you can share your slide.
Oh, so can you see my screen?
Yes, yeah.
All right. Okay. So hi everyone. I'm TA Jimmy. So in the following slide, I'm going to announce homework number 4. So as the previous homework, we have 2 weeks. So the deadline of homework 4 will be May 25, Wednesday. So you will also need to finish the code assignment and and write some short answer questions. So please remember to submit your code and your reports on the UC system. You can find the sample code and the questions Google document in this link. So in the homework number 4, you need to implement the cross-validation and the hyperparameterization for SVM model training. So please remember to follow the file naming rule here. 那各位同学好，我是居民。那我们这个简报会公布作业式。那跟之前的作业一样，我们会有2周的时间让同学完成，所以是下礼拜后的下礼拜3，所以是5月的25号。那一样我们会有2个部分，在作业式2个部分会有一个是 coding 的部分，同学必须去实做 cross validation 跟 hyperparameterization，那去用这些技术来帮助你的 SVM 来找到合适的参数。那第2个部分则是一些简答题。因为这次的话，因为SVM 的 coding 的部分相对是比较简单的，所以我们就是把 coding 的分数调成50%，然后简答题的部分的数量也会稍微多了一些，那就是让同学就是这次作业的 loading 跟之前也是差不多的。So for the support vector machine, I try to find the best hyperplane to separate the different classes in different dimension. So your target try to separate the different classes, but it turns out there are a lot of hyperparameters to be tuning. So in this homework, we introduce like research and cross validation to help you to find the best hyperparameter. So since SVM requires a lot of difficult mathematical operation, we will not ask you to implement SVM in this homework. So you no need to implement SVM. You can directly call the SVM module from the scikit-learn. 那在 SVM 这次的作业里面，因为它牵扯到比较多数学的问题，所以我们这次不会要求同学去实做 SVM 的数学细节，而是可以直接使用 scikit-learn 的这个套件。那但是我们在 SVM 实作过程中，它有很多参数要调，所以这会请同学用 NumPy 来实做调整参数的整个过程。So there are lots of hyperparameter SVM, so you need to implement the research and the cross validation to find the best hyperparameter of SVM on the provided dataset. So in this one, you need to research and cross validation. So first, we introduce how do you do the hyperparameterization. So suppose we want to find the best value of 2 hyperparameters, say namely for RBF kernel SVM. So namely is C and gamma. You can find this interactive demo to show when the C and the gamma how the accuracy and the hyperparameter and the separate hyperplane will be changed in different combination of these 2 parameters. So you can see like suppose the y-axis is the C and the x-axis is the gamma. You can see that the different number will show the different classification result. So you can see this reference for more details. 那在这个作业中，我们会要介绍一个 hyperparameter searching 的方法，那就是假设我们要找到两个在 SBN 面 RBF 的 SBN 中 C 跟伽马这两个参数的时候，可以看到这两个参数其实对于我们最终的 accuracy 是会有影响的。所以同学就是可以去点到这边的 demo 会这边网站会秀说这两个参数是怎么样去影响到你这个整个模型最后分类的结果。So the naive way to do the hyperparameter search is the grid search. So it just exhaustively consider all the hyperparameter combination and pick the best one based on the model that gives the best performance. So suppose we want to find the C in the three values, 0.1 and 1 and 10. And for the gamma, we want to search for these four values, 0.1, 0.1 and 1 and 10. So since there will totally be 12 combination for this tuning. So C is here and the gamma is here. So we will have 12 combination. So we just pass this parameter as the model parameter and then train your model on this parameter and to see which one give you the best performance, and then we suppose this one is the best performance. So we can use this as the final parameter for our model. 那一个最直观的方法，就做个 parameter searching，就是你用暴力的方法去搜寻。所以简单来说，我们把我们的 C 设置在一个0.1跟1跟10这三个数值，然后伽马是0.01、0.01跟1跟10这四个数值，然后我们就把这四个数值，这12个数值，这三个 C 跟这4个伽马做一个排列组合，把它们所有可能性列出来。那我们就把这些参数全部丢进我们的模型去跑，然后就可以得到看看哪一个效果最好，那就是我们最终想要的一个参数的结果，所以这是个最简单的 grid search 的方法。And then we will and when performing the grid search, usually we will use the K4 cross validation. So that's we will split the data set into the K parts. So we have the training set here. We separate it into K parts. And one part is used for validation, and the remaining K minus 1 parts are merged into the training subset. So suppose for here, we split it into like 5 parts, and the first part will be the validation set, and the rest of data will be used as the training subset. So this process will repeat K times. So when for each time we can see that the validation fold will be different. So each part will be used exactly once as the validation data. So you can see see the video here. You can see that suppose we have 12 data points and the K is 3. So you can see that the test set will be like this one and this one and this one. So we can see that the validation will be only used exactly once as the validation data. And after that, we can train our model. So we train our model on this subset. We test this model using this validation fold. We can get a performance 1 here. And for the next iteration, we can get another performance 2. And after that, we can just average this performance. So this performance is actually the average of this of all of this validation folds. So when using the K4 cross validation, we can use all of the data as the test set, and we can get more average score here. 那这边有个 K4，在做 grid search 的时候，我们通常会使用这个 K4 的 cross validation，就是避免说我们都重复使用同一个 validation data。那这个 validation data 可能它就在过度使用之后，就可能会产生 overfitting 的情况。所以呢，我们在这个使用 K4 cross validation 的时候呢，我们先将 data set 切成 K 个 part。那在切成 K 个 part 之后呢，我们通常会使用其中一个 part 当做一个 validation。那剩下的 part 呢，我们就把它 merge 成一个 training 的 fold。所以在 K 等于1的时候，我们在进行第一次的时候，我们会用第一个 part 当做 validation， 剩下4个 fold 当成 training 的话，这时候我们用我们其中一组参数进来，然后训练完之后，我们得到了一个 performance。那接下来的话，我再用第二个 part 当做 validation fold， 剩下的4个 part 呢当做 training。所以这样重复的做了之后，我们会发现 每一组的资料都在我们整个圈链上面，每一组资料都轮流当过一次的 validation data。那之后我把这个结果呢平均起来，我们就可以得到一个更平均的结构，而不是说我们只用比如说只用第一组这一组的资料，一直重复使用同一批资料当做 validation data，导致会有可能 overfitting 的情况产生。So if we combine the cross validation with the hyperparameterization, so as in the page C, we we can experiment with this 12 combination of the hyperparameter. So suppose we have the first combination, the C is 0.1, the gamma is 0.1. We use this hyperparameter to perform the K4 cross validation. So that is, we use this validation data and this training for, and we train this model using this hyperparameter. So we can get that the average score is 0.8. And for the second combination, we have 0.1, C is 0.1, gamma is 0.1. We again use this K4 cross validation, we can get the average score is 0.91. So after we loop all of the combination, we can find the best combination which will the best performance. So in this case, the best performance is from the combination 2, which is C is 0.1, gamma is 0.1. So we can know that this hyperparameter is the best one. And after that, we just use this combination, we can just use this hyperparameter to train your model on the whole training set. So after training, we can just evaluate on the rest test set. And please know that this test set is not involved in the whole K4 cross validation. The test set is different from this validation and this training for is just split before we perform the K4 cross validation. 那怎么样把这个 cross validation 跟我们前面提到的 hyperparameterization 做结合呢？那比较简单，就是我们刚刚在前面提到有12组参数的组合，那在每一次的组合呢，比如说这个第一个组合的时候，我们就把这个组合拿下去跑 K4 cross validation。所以就是在每一次的 K4 的每一组资料训练当中呢，我们都用这组参数去做。那我们会得到5次的结果，把它平均起来，你就可以知道说这个参数组合1，在这一次的 K4 cross validation 得到的平均结果是0.8。那第二个参数组合跑出来的结果是0.91，然后我们第一次就把所有的定义好的组合全部跑完。那哪一个组合可以得到最高的平均结果的话呢？我们就认为说这个参数组合是一个最佳的结果，因为它在每一个资料当做 test 的情况下呢，当做 validation 的情况下呢，都能得到不错的，都能平均下来可以得到最好的结果。所以这个参数应该是一个相对比较稳定，而且比较不容易 overfitting 的参数。那在最后我们找到这个参数之后呢，我们就会拿这个参数训练在我们的整个资料集上面。那这个差别是差在说，我们原本整个资料集是我们切了一小部分做 validation 的，但是我们已经当我们找到一个最好参数之后呢，我们就相信这个参数是最好的，所以我们就把这一个参数训练在整个圈内 set 上面。那一开始我们在做我们训练的时候，我们通常都会把资料切成圈跟 test， 所以这是有一笔这时候会有一笔 test set 是完全一开始在我们做 K4 cross validation 的时候都完全没有使用过的资料。那这时候呢，我们再去看说这个 test set 上面有没有发生很明显的有没有发生很明显没有的 overfitting 的情况。那通常的话，因为我们这个参数是经过 cross validation 的选出来的，所以通常其实不太会有这样的，不太会有overfitting 的情况，所以我们就通常认为这个参数会是最好的结果。Okay, so for the more detail of the K4 cross validation and research or the SCP hyperparametering, I provide these two reference link for your reference. So just as usual, we will deduct the late policy will be just as usual. So please know that do not submission late your homework late, and please submit your homework on the UC system. And if any questions or comments, please feel free to mail me and CC Professor Lin. So that's it for this homework number 4. If you have any questions, feel free to ask. Thank you. 那就是这个就是作业室的介绍，如果同学有任何问题的话，欢迎询问。那这边就给同学看一下，就是这一次的作业的 Google document， 所以基本上就是有5题的程式题，4题的程式题，然后包含5题的手写题这样子。所以这些就是介绍，就是要同学实做 K4 cross validation 啊，还有你的 research。 然后把你们的归社区的结果画成刚刚那个表格的结果，把它画成一个像是这样热度图的方式，呈现出每一组组合它的最终的 performance， 然后最后就是希望同学可能够找到一个最好的结果，得到一个比较高的分数。好，那以上就是作业式的介绍。
大家对作业室有没有什么问题呢？Is there any question about homework number 4? Jimmy 好像有同学是在那个对话方块里面问的。Jimmy 你有看到吗？
我看到，可以。不过我们应该有都帮同学是做完了。如果你觉得你的 performance 没有达到的话，是你可以去做额外的 data preprocessing 是没问题的。可以使用 Matplotlib 去画热度图，这个在那个里面会有说明。OK。
如果没有其他问题的话，那我们今天的课程就到这边哈。If there is no further question, it is about time to complete the lecture today. Thank you for attending today's lecture.